Hi, my name is Noah Arliss, a Senior Development Manager at Oracle, and today we're going to talk about how you can harness the power of Oracle WebLogic and Oracle Coherence to simply and easily build real-time processing systems. Before we begin, I'm required to inform you that the following is intended to outline our general product direction. It is intended for informational purposes only and may not be incorporated into any contract. It's not a commitment to deliver any material, code, or functionality and should not be relied upon in making purchasing decisions. The development, release, and timing of any features or functionality described for Oracle's products remains at the sole discretion of Oracle. Here's the agenda for today. I'm going to provide a little bit more detailed overview. We'll talk about the building blocks of event-driven architectures, coherence and WebLogic integration in the context of coherence managed servers, WebLogic, WebSockets, and Avatar, and finally we'll go through the code to build a processing system based on Twitter. So let's talk a little bit in more detail about what we're going to go over today. I'm going to start by introducing the notion of event processing systems and event-driven architectures. I'm going to talk about two key features, namely map listeners and live events, and how they are the cornerstones for building event-driven architectures using coherence. We'll talk about the coherence managed server integration, which is basically the tight integration between coherence and WebLogic, allowing for simplified development lifecycle, reasonable and intuitive deployment models, and simplified operational management. We'll talk about how you can leverage WebLogic, WebSockets, and Project Avatar to create a dynamic presentation layer for a real-time processing system based on coherence. And finally, we'll tie that all together with application code and a demo that will show processing events in real time from Twitter and how we can visualize them over a web interface. So let's talk about event-driven architectures and coherence. Before we begin, I'd like to go into event processing 101. In essence, when we build an event processing system, it's all about reacting and responding to events. We need to decide when something is notable and then take some action. Often those actions may lead to additional downstream events, which may lead to additional downstream actions. In an event-driven architecture, it's important that there's a loose coupling between events and their actions. This allows for a highly distributed system where things aren't related to one another. And what it means is that events need not and should not be aware of their consequences or their actions. When we build a real-time system, often we're responding to many events all at once, and therefore it's important that these systems be highly distributed in nature. There are three categories of event processing systems. The first is simple event processing, which is often what real-time systems are based on. Something noteworthy happens and some action is taken downstream. There's stream event processing, where all events are delivered to the system and screened for notability. And finally, there's complex event processing, which is the confluence of events over time, which allows for the causal and temporal and spatial correlations. We're going to focus today on simple event processing or real-time systems. The building blocks for event-driven architectures in coherence have two key elements, map listeners and the live events feature. Starting with map listeners, which allow you to, as an application developer, respond to changes in data as they occur. Map listeners are executed asynchronously in response to CRUD operations. In the diagram to the right, you'll see that the application on the right has made a modification to an element in the cluster, and the other two applications have been notified that that modification has happened. Map listeners can be registered with filters to selectively process only some elements in the cluster, and they're often used for application-side processing. There are three key elements to map listeners. First and foremost, there's the observable map interface. This is the interface that allows you to add and remove map listeners. And if you work with named cache or you're familiar with named cache, the named cache class implements the observable map interface. The next is the map listener interface. This is the interface as a developer that you'd implement to respond to those notifications as data is changed. And finally, there's the map event class, which gives you information about the event and what happened. The second building block for event-driven architectures in coherence are live events. Live events are the rationalization of one simple concept. All applications have a need to intercept, override, and respond to events in a consistent and unified manner. They provide a consistent server-side framework for configuration, representing, and interacting with every type of event within Coherence. There are 4 classifications of live events today. There are entry-based events, which allow us to respond to changes to entries within the cluster. There are entry processing events, which allow us to respond to the execution of agents against entries, namely entry processors and aggregators. There are entry lifecycle events, which allow us to respond to the movement of entries within the cluster. And finally, there are entry transaction events, which allow us to respond to a transaction, primarily the transaction light framework within Coherence, where we'll get a set of entries that have been modified in the context of that transaction. Today we're going to focus primarily and solely on entry-based events. So when we talk about entry events, they are server-side pre- and post-entry mutation events. You get a set of entries that have been modified, and then there's a type: inserting, inserted, updating, updated, removing, and removed. All the pre-events happen before the entry has been committed to memory, giving you the opportunity to potentially mutate that entry before it's been committed to memory, while the post-events are triggered after the changes have been committed to memory, and therefore you no longer have the opportunity to mutate them. As a consumer of live events, you need to implement the Event Interceptor interface. It's an easy to implement interface where you can annotate the entry events that you're particularly interested in, which we'll see when we look at the code in more detail shortly. But the interface itself is very simple. There's a single event to implement on event. Semantically, here's what it looks like when you work with entry-based events. When a client does a put on an entry in the cache, you'll get an inserting event before it's been committed to memory, giving the Event Interceptor a chance to interact with that object before it's been committed to memory. Once it's been committed to memory, the inserted event will be fired asynchronously at the same time that the backup is fired. Once the backup completes, the coherence will then return to the caller. That concludes the 2 major building blocks for event-driven architectures in Coherence. We'll see more detail on those objects as we look at the code base in a few minutes. Let's talk about Coherence Managed Servers now, which is the tight integration between Coherence and WebLogic that was delivered as a part of the 12.1.2 release. Coherence Managed Servers were built primarily to simplify the development lifecycle and operational management of Coherence clusters. It starts by introducing a key building block, which is the grid archive. A Coherence grid archive follows the Java EE model and consolidates configuration, domain objects, and cluster-side processing into a single distributable entry. This simplifies what you're going to put into your deployment processing, as well as how you can deal with the lifecycle of your application by having a single object build artifact to work with. A grid archive also provides application isolation and lifecycle events. By introducing a grid archive and tightly integrating with WebLogic, Coherence can now leverage all of the WebLogic infrastructure that's available. Similar to EJB, JMS, and JCA, we now have the ability to manage a Coherence cluster using the Configuration Wizard, WebLogic Admin Console, WLST, JMX, Fusion Middleware Control. We can deploy our applications while the JVMs are dynamically running. Node Manager is available to us for process lifecycle management. And finally, if you're working with WebLogic, you no longer have to deal with putting Coherence libraries on the system class path, as they're already there for you. You'll see here that the difference between a standalone cluster where you have Coherence servers and a WebLogic domain managed cluster is that now the Coherence cluster is a part of the domain and a part of a managed server that's running within that domain. Let's talk a little bit more about a grid archive, as it's a key concept in this new model. A GAR file contains all the dependent artifacts required for the operation of a Coherence application. The structure of a GAR is as follows. You have a GAR deployment descriptor, a cache configuration file, a POF configuration file, and any and all classes required by the Coherence application: entry processors, POJOs, business logic, serialization or domain objects, and finally any supporting libraries. The GAR deployment descriptor describes a few key elements related to the application. Namely, it gives a pointer to the configuration file that should be used, including an optional override property, a pointer to the POF configuration file, and finally, if you want to override the configurable cache factory that's used. In addition to the grid archive, there's a tremendous advantage to working with Fusion Middleware 12.1.2, in particular the Maven integration, which truly does simplify the application lifecycle and developer end-user experience with respect to working with Coherence and WebLogic. There are 3 levels of support: the Maven Sync plugin, which integrates Coherence and the rest of FMW into your own Maven repository; the GAR archetype, which allows you to generate a new Coherence project using Maven; and finally the WebLogic Maven plugin, which allows you to operationally manage and deploy actions within WebLogic. We'll see all of these in action as we get into the actual code and demonstration of the application. Let's talk about deployment models, because we need to understand deployment models before we talk about best practices. There are 3 typical deployment models for working with a grid archive. The first is standalone. If you have managed servers, which is typically the best practice, that are going to be responsible for being cache servers, you typically would deploy GARs to those. Each GAR provides a sandboxed, isolated space within a managed server. So if you deploy 2 GARs, myapp.gar and myapp2.gar, to the same cache server, those applications won't see anything about the other application that's running. In addition, you may embed a GAR within an ear. This embedded GAR makes those classes that you've embedded available to WAR and JAR files, and also allows for the same grid archive to be worked with either in the client side or the server side. Finally, if you want to share a grid archive amongst multiple ears, you can deploy it as a shared library. From a best practices point of view, now that we understand deployment models, we like to have a tiered architecture. In particular, we want to separate out the application tier from the cluster tier or the caching tier by having the application tier be storage disabled. Namely, we don't want the resources responsible for hosting and running an application to interfere with the resources responsible for hosting and managing caching. In the diagram below, on the diagram to the right, you can see we can utilize WebLogic clustering capabilities to manage this. What I mean by that is we have 2 WebLogic clusters. We have the web tier and the data tier. The data tier is configured to be storage enabled, where the web tier is configured to be storage disabled. On the web tier, we deploy our ear that has the GAR in it, which allows all of these managed servers to be working together, because in the data tier we have the same GAR deployed, and because we have the same GAR deployed, we have all the same configuration and classes available. Managed server 1 through managed server 6 are all a part of the same cluster, namely the same Coherence cluster, but they're 2 different WebLogic clusters, one for data and one for applications. Now let's talk a little bit about WebLogic, WebSockets, and Project Avatar. WebSockets is a good place to start. WebSockets provide for full duplex communication over a single TCP connection. What this means is I can have a dynamic bidirectional communication over a single socket between a web browser and a web server. They were standardized by RFC 6455 in 2011 and have been designed to be implemented in web browsers and servers, and can be used by any client or server application. Messages, when we're working over WebSocket, often are written in JSON. In WebLogic, now with WebLogic 12.1.2, you can actually implement WebSockets using standard Java classes. In particular, you use a special WebSocket annotation and implement the WebSocket adapter interface. Here's a sample block of code where we've annotated the message listener class with a WebSocket that has a timeout of 5000 and a path patterns of /ws. You'll note that the message listener extends WebSocket and implements the onMessage method. On the client side, typically clients are responsible for creating a connection to a URL, registering listeners for events, namely on open, on message, on close, and for sending messages over the WebSocket. Avatar components, which we'll talk about next, have been designed to handle and work with WebSockets directly out of the box. So let's talk about Project Avatar. Project Avatar is an end-to-end application framework based on thin server architecture. It was designed to build modern HTML5 applications by leveraging Java EE as a platform. It supports two key elements, view components and server components. So a little bit more detail on the Avatar architecture. There are model components, view components, and widgets. A model component is a JavaScript object that's responsible for containing application data. View components, which are new and traditional HTML elements supported by the framework, bound to the model and are responsible for rendering data, and widgets, which are pre-built view components that provide functionality out of the box, like bar charts. One of the models supported by Avatar out of the box is the WebSocket model. Conceptually similar to classes where you need an instance, a model defines variables which can be referenced by an expression language as described on the earlier slide, and $prefixed functions which are called by the framework for specified events, for example, leading with the WebSocket interface on open, on message, and on close. An avatar view, as we talked about, are instances of models, and in the case of WebSockets, they bind to a specific URL. And finally, we can then actually take the widgets and work with them. Either we can have just standard expression language that we embed in the HTML in the example of TWC model server query, which is the first code sample, or we can have a widget like this chart where we're going to take TWC model members and TWC model cache sizes and render those in a bar chart. This will all make much more sense once we get into the code base. With that, let's get into the code base and talk about the real-world application for processing events from Twitter. Before we begin, however, I want to give you a little bit of an overview of the architecture. What we've built is an actual application. Everything in this diagram is either running inside of Coherence or inside of the web browser. On the top, we have the Coherence cluster-side event processing system. In essence, we open up a listener that's listening in the Twitter universe for statuses based on a hashtag we're interested in. As those status objects come in, they get written to the status cache. Within the status cache, we have a status interceptor. Its job is to take any and all tags that have come in on a status object and to put them into the tags cache. As a part of putting them into the tags cache, we keep track of the count, or how many times we've seen that tag show up. There's more processing that goes on in the tags cache that allow us to actually continue to broaden our search. Not particularly relevant for this talk. On the bottom side of the screen, what we have is sort of the server and client interactions. There are two key rendered elements that we're going to show in Avatar in the browser, a bar chart and a word cloud. The bar chart shows the Coherence members and how much data they're holding, and the word cloud shows all of the tags, and the size of the words in the word cloud are based on the count of tags that we've seen coming in from Twitter. Finally, there are control functions that are also sent over the WebSocket. Based on our event-driven architectures, we've got interceptors that are actually responding to events from Twitter, and we've got map listeners which are responding to events from Coherence and rendering those events or sending those events over a WebSocket to be rendered in the browser. So with that, let's talk about some application code. Here I have my application code inside of the IntelliJ IDE. I'm actually going to start by deploying the application so you can actually get a sense of seeing it in real time, and then we'll come back and look at the details. To do that, I'm actually going to take advantage of the WebLogic Maven integration, in particular the WebLogic Maven plugin, to do my deployment. The deployment information is defined as a part of my standard POM file configuration. Namely, I'm going to be using the Oracle WebLogic Maven plugin. I've configured where my admin URL is. I've given it a username and password, which I don't have to provide, but as an engineer in the development environment, it makes things pretty easy. And what I've done is I've deployed that to my data tier. And I'll show this to you in the GUI in just a second. Now that my GAR is deployed, let's deploy the ear as well, again using the WebLogic plugin. So we'll select the WebLogic deploy operation. Again, looking at the ear, we'll see that the POM file has a WebLogic Maven plugin defined in it, a admin URL host, and a target. In this particular case, it's the application tier. So we'll see that that completed successfully. If we now look in the browser and we look at deployments, what we should see first and foremost is that I have an ear and a GAR file deployed. And you'll notice that the ear is deployed to the application tier and the GAR is deployed to the data tier. And if you want to look a little bit more closely at my environment, we'll see that there are two clusters defined, an app tier and a data tier. The app tier has 2 application servers bound to it, and the data tier has 3 application servers bound to it. If we look even a little bit more closely at the data tier and we look at the Coherence tab, you'll find that local storage is enabled for the data tier. If we look at the application tier and we look at the Coherence tab, what you'll find is that local storage is disabled. Let's get back to looking at the application. So if we go look at deployments, we can see that my ear is deployed. The ear actually contains the modules for the application, which consist of a web app and a Coherence archive. For a testing point of view, we actually want to dig into the details of the web app. So if we follow that and click on the testing tab, we'll find that I have an application server running. So let's connect up to that application's test instance, and what we'll see is actually a rendering of our word cloud example. At the moment, nothing is running. If I start with a simple hashtag search on Twitter for now playing, which is a fairly common Twitter theme that's running all the time, and I enable my application, what we should see happen within the next couple of seconds here is that Coherence is now going to open up and we're going to see real-time word cloud moving based on the results that are coming in from Twitter. On the bottom we'll see a bar chart that's rendering the number of objects that each cluster member is containing, and at the top we're seeing the word cloud move as the results are being processed. Now let's have a look at the application code to see how this was built, and we'll come back and play with the application again in just a few moments. Coming back to the application, I want to focus on the GAR file first. As we discussed in the slide deck, the grid archive truly simplifies the development lifecycle. If we drill into the contents of the grid archive, what you'll find, first and foremost, is a set of dependencies that the grid archive needs in order for the application to run. In particular, we have a dependency on the Twitter for J API, which is what we're using to connect up with and communicate with Twitter. What we've done here is we've taken all of our dependencies, Twitter for J, JSON processing, and everything else, and embedded them within the same GAR packaging. As I described, all of our distributable components can be embedded in the GAR, making it very simple to take a single artifact, to deploy, and to manage it. Let's drill into the implementation of the grid archive. If you expand the Java source tree, you'll see many packages to work with. We want to focus today on the interceptors, in particular the status interceptor. Implementing an interceptor is a relatively straightforward process. We start by annotating the object, uniquely identifying it, and specifying the type of events that we're interested in receiving. And then we implement the event interceptor interface, which is a single one-method implementation. Let's break down what the onEvent method is doing. If you recall, the status interceptor is responsible for listening for status objects that have been inserted into the cluster as a part of listening to Twitter. All status objects potentially have hashtags associated with it. So what this method needs to do is it needs to take the hashtags off of the status objects and insert them into the tags cache, keeping track of the number of times we've seen that particular tag before. So let's break down the implementation in more detail. The first thing we do is we get a reference to the tags cache that we're going to be working with later, and then we iterate over every entry in the events entry set. The first half of this for loop is responsible for getting the status objects hashtags and putting them into a set. The second half of this for loop has some very interesting coherence functionality in it. What we do is we create a composite entry processor. The composite entry processor starts off with an array of entry processors, and this array has two entry processors in it. The first is a conditional put. What it will do is check to see if a key exists in the cluster, and if the key is not present, then we'll insert that key with an initial value of 0. The second processor does a simple number incrementer of the value. So if the key doesn't exist, we'll insert it with a value of 0, and then we'll increment it to a value of 1, meaning that all keys that gets inserted into the cluster start with a value of 1. If the key already exists in the cluster, however, we'll skip the insert from the conditional put and we'll just increment its value. Let's take a look at the cache configuration. To do that, we're simply going to look into the resources of the grid archive and have a look at the cache config. In particular, I wanted to show you the cache scheme mapping definition for the tags cache. Interceptors can be registered as a part of the cache scheme mapping. So our tags interceptor is registered as an element within the interceptors block of the cache mapping. This means that the tag interceptor will be triggered anytime entries are modified on the tags cache. Let's recap what we've looked at here with respect to the grid archive. We've seen the cache configuration where the dist tags cache has the tag interceptor registered on it. We've seen the status interceptor implementation, which is responsible for pulling hashtags off of status objects in the status cache and putting them in the tags cache. We've seen the POM file configuration, where we've pulled all of our dependencies into the single distributable archive, the grid archive. And we've seen that we can deploy functionality directly from Maven into WebLogic. Let's now move on to the web side of the implementation. If you recall, the application is comprised of an ear that contains the Twitter feeds gar and a Twitter feeds war, and that's what we deploy to the application tier. And the data tier, or the caching tier, just has the gar deployed. Let's now have a look at the web archive. I want to start by looking at the front side, or the client side of the application, the HTML and JavaScript, and then we'll work our way back to the back end of the implementation, or the coherence side of the implementation. So if we look at the word cloud HTML, it's a relatively simple set of JavaScript and HTML elements, but there's quite a lot that's going on here. First of all, we're including some sources from WordCloud.js and Cloud.js, which is a third-party word cloud library that was used for the case of this example. The real important part, however, is the data model, which is a WebSocket-based data model that defines the following data elements. It defines whether it's enabled, it defines the query string that's being used, it has the set of tags that are found for the given search string. Then we have two elements that are used for the bar chart, the number of members of the cluster and the sizes, or the number of elements that are held by each member. Moving down to the $ prefixed methods, the onOpen and onMessage methods. The onOpen function will be called when the WebSocket is opened between the client and the server, and we basically use this open element, or this open event, to send commands to and from the server. The onMessage function is where all the magic happens. In essence, when we receive a message, the first thing we do is save off our current view of the tags elements, and then we process the method that's come in, the message that's come in. After processing the message, we check and see if the tags are one of the elements that have been updated in our model, and if the tags have been updated, then we're going to generate the word cloud, which will cause the word cloud to be redrawn. And that is what shows the motion when we look at the actual client or we look at the result in the web browser. Moving down further, what we can see that now we can instantiate our model through the data type script element. In essence, this takes the word cloud model, binds it to a TWC model data instance based on the URL Twitter feed /twc.ws. When we look at the application side or the server side of the implementation, we'll see that the WebSocket is going to be listening or configured via an annotation to be listening on twc.ws. Now that we have an instance of the data model, we can use that data model in our views, whether we're using it directly in HTML like this, where we're taking the server query element and just writing it out in HTML, or whether we're calling methods on buttons like here, where the enable button is calling the switch enable method on the TWC model, or finally whether we're using those elements inside of a widget like our bar chart, where we're taking members and putting them in the x-axis, and we're putting the TWC model cache size in the series point label section of the widget. Moving to the back end of the implementation, we can see, starting by looking at the word cloud WebSocket, that we have annotated the object to listen on twc.ws, and we've implemented the WebSocket adapter. For the sake of this talk, we're going to skip over the rest of the WebSocket because it's primarily focused on dealing with parsing of JSON objects and instantiating coherence map listeners. If we look at the tags map listener, again we're going to see a fairly straightforward and simple implementation. We have a map listener that implements the map listener interface. We keep a copy of the connection to the WebSocket that was created as a part of the instantiation of our WebSocket object. We have a reference to the name the tags cache, and then we keep a local copy of the tags map. The reason we do this is for performance reasons. Because our word cloud is being used to render all of the tags that have been stored within Coherence, we want to prevent ourselves from having to get every single element in the tags cache every time. In essence, a get all is a very inefficient way of doing things. By keeping track of the tags in memory, we can prevent doing a get all, and instead just focus on the particular tags that have been updated at any given time that an event gets called. So let's have a look at the actual implementation of the map listener. In particular, you'll see there are three methods on the interface. If an entry has been deleted at this point, there is no actual opportunity for that to happen in this particular implementation, so we don't have an implementation for deleted. On inserted and updated, we actually will take the key and the new value out of the map event and put it in the tags map, and we'll call update web. For entry updated, again, we get the key and we get the value and we put it in the tags map and we call update web. The update web method is responsible for taking the tags map and putting it into a JSON results object, and then finally we create a JSON object called tags that is the combination of the element tags plus a result. Once we have our JSON object, we actually send it over the WebSocket connection, and that delivers it to the avatar WebSocket model, which can then be used to regenerate the word cloud. So now what I'd like to do is tie everything back together. We've looked inside of the implementation of the web app, and we've taken a look at the word cloud HTML, which is responsible for binding avatar to a WebSocket and for rendering the dynamic application that we've seen in our browser. We've seen the Twitter word cloud WebSocket, which is bound at twc.ws and implements the WebSocket adapter interface. We've seen the tags map listener, which is responsible for listening for updates on the tags cache and sending those over a WebSocket connection to the avatar WebSocket data model, which gives us an entire comprehensive web application. By combining the web application with the grid archive, we're able to see and create dynamic event-driven architectures using coherence and WebLogic. Let's take a look at that application one last time. If we enable the application, you'll see that we've built a real-time event processing system using coherence and WebLogic. We have all the advantages of being able to control the lifecycle and deployment of our applications, leveraging all of the WebLogic infrastructure through the WebLogic console, WLST. And we've got all of the advantages of using coherence, including the ability to use map listeners and live events to create real-time event processing systems. With that, I'd really like to thank you for joining us today. Join us at coherence.oracle.com on Twitter, Facebook, or see more content on our Oracle Coherence YouTube channel. Thank you.